Alright, I want to talk about climate, and it's really important to discuss climate because it has a lot to do with how organisms are interacting with their environment and, the ability just to survive in general. So there's actually a lot of cool information here. And to start off, I just want to say that, the geographic variation in climate, primarily temperature and precipitation, govern the large-scale distribution of plants and therefore the nature of terrestrial ecosystems. So climate determines the availability of both heat and water on the Earth's surface. And that's important because it governs this distribution of plants. And we all know that plants are kind of the beginning of the food chain. They're sort of that beginning of the cycle, at least for the terrestrial animals. Because as humans, we don't make our own food. We have to consume other animals, plants, etc., in order to gain the energy necessary to survive and the nutrients necessary to survive and function. Plants are extremely important, and where they're going to grow is going to be determined by the temperature and precipitation, two important factors of climate. So, Earth intercepts solar radiation, okay? And the Earth's atmosphere intercepts solar radiation on its outer edge. Okay, the resulting molecular interactions creates heat and causes thermal patterns that, coupled with the Earth's rotation and movement, generates winds and ocean currents. So this solar radiation, along with the Earth's rotation, okay, around the sun and on its axis, allows allows for this generation of both the winds and the ocean currents, okay, two important determinants of climate. And these movements of air and water in turn influence the Earth's weather patterns, okay, including the distribution of rainfall. So all these things have to do with why the Earth's climate is the way it is, or why the place where you live might not be the same as the place where I live, okay, why I may get more precipitation or less precipitation than you. So a hot surface like the sun gives off primarily short-wave radiation, okay? And in contrast, cooler objects such as the surface of the Earth give off long-wave radiation, okay? And they're just speaking strictly about the wavelength, all right? The wavelength is the distance between successive crests or troughs, okay? And of the solar radiation that reaches the Earth's atmosphere, only 51% of it makes it to the surface. So not a lot of it's actually making it to the surface. I mean, it may be intuitive that, yes, the Earth gets solar radiation from the sun, okay? That's totally intuitive. But what may not be intuitive is that the Earth actually reflects just as much radiation as it absorbs. The only difference is the type of radiation, okay? The Earth is giving back off or reflecting long-wave radiation, while the sun is giving off this short-wave radiation that's being absorbed by the Earth's surface, okay? So, that's not so intuitive. And the fact that it only absorbs 51%, it has to make you think. I mean, that's not a whole lot of the energy. I mean, there's a lot of energy there that's being lost, and we're going to talk about where it's being lost next. So the atmosphere, and that's what I'm going into here, the atmosphere and clouds absorb a great deal of the radiation, okay? The atmosphere and clouds absorb a lot of this radiation. It never makes it to the surface. And the Earth's surface reflects some energy as well, okay? Now, one of the things everybody hears about in the media and the news, and as well as if you're involved in the scientific community, you hear about this greenhouse effect, okay? And everybody might have an idea of what the greenhouse effect is. It has something to do with carbon dioxide. But the atmosphere only allows a small fraction of energy to be passed through into space, okay? The majority of the reflected energy, so now I'm talking about the long-wave radiation reflecting off the Earth's surface, so majority of that reflected energy of the Earth's surface is absorbed by CO2 and water vapor in the atmosphere and clouds. Okay, so again, the atmosphere and clouds and this carbon dioxide is absorbing a great deal of that energy. And then what happens to that energy? Well, the energy is radiated back to Earth, okay? And that produces the greenhouse effect. So that's how you produce this sort of warming effect. I mean, this is a concept that people were even saying could work on say, a place like Mars. If you went to Mars and you created a lot of carbon dioxide, a lot of so-called air pollution here, you might actually be able to warm the surface by doing so, okay, by using this greenhouse effect. So the radiated energy that's absorbed by the clouds and the CO2 is radiated back to the Earth, and that produces the greenhouse effect, which is crucial for maintaining the surface warmth of the Earth. So as you can see, it's extremely important to have this greenhouse effect. It's crucial for maintaining the surface warmth of the Earth. But on the other hand, it also can get out of control. If we have too much energy being reflected back, too much radiation being reflected back onto the Earth's surface, it can warm the planet too much. And that's sort of where they get this idea of global warming from. I mean, at least in a very broad and general sense. This is not a whole lot of detail, but it's enough for you to be able to maybe talk to somebody about global warming and explain why it's happening and why carbon dioxide is important to control. And you know, the Earth receives a great deal more long-wave radiation than short-wave radiation, okay? And that's what I was talking about before. That reflected energy back off the atmosphere and CO2 ends up in the form of long-wave radiation, okay? So, intercepted solar radiation varies seasonally. Alright, the amount of solar energy accepted at any given point on the Earth's surface varies with latitude. Okay, so that's extremely important. It varies with latitude. So two factors that influence this variation. First, at higher latitudes, radiation hits the surface at a steeper angle, spreading light over a larger area. Okay? And second, radiation that penetrates the atmosphere at a steeper angle must travel through a deeper layer of air. So this explains decreasing temperatures from the equator to the poles. So as you go up in latitude, as the latitude increases towards the northern or southern poles, you're going to wind up having the sunlight dissipated over a larger area, and it's going to have to travel through more atmosphere, which means more of it's going to get absorbed before it hits the surface. So what does that mean? If more of this energy is getting absorbed by the atmosphere and carbon dioxide, etc., and clouds and water vapor, then not as much of it's going to hit the surface. And if not as much of it's hitting the surface, then it's not going to be as warm. So plain and simple. Okay? If you're talking about people who live at or near the equator, they're going to have, you know, sunlight that's not traveling through as much air, that's not hitting the Earth at a weird angle, and thus it's going to heat that area much more efficiently. Okay? And that's exactly what I'm saying here. So this, however, does not explain the seasons, though. Okay, so that doesn't explain why, you know, where I live, I have all 4 seasons. I have a summer, a winter, a spring, and a fall. Okay, so the reason where we experience hotter days in the summer and colder days in the winter is because the Earth does not stand straight up. Rather, it's tilted on its side. So this is like, this is really, really simple concept when you think about it. It's just because the Earth is tilted on its side. It's tilted on its axis. It doesn't sit straight up. Alright, and that has to do with the Earth's axis of spin is not perpendicular to the elliptical, but it's tilted at an angle of 23.5 degrees. So the angle is 23.5 degrees. So essentially what I'm saying by that is the Earth doesn't sit straight up like this pen here. It's actually tilted at about 23 degrees, so I don't know, something like that. Whatever, it's tilted on its side. It doesn't really matter. Okay? So it is that tilt that gives rise to seasonal variation in temperature and day length. So it's that tilt that gives the rise to seasonal variation. So if somebody asked you, why do we have seasons? You would just say because the Earth's tilted on its axis at 23.5 degrees. Okay, it gives rise to seasonal variations in temperature changes. Okay? And day length as well. So another interesting question that you may have thought about, or maybe you haven't thought about, is air temperature decreases with altitude. So how come as you go higher and higher, if you're climbing Mount Everest, as you got higher and higher, how come the air temperature decreases? I mean, it kind of makes sense. You say, well, the top of a mountain has snow on it. It makes perfect sense that it's colder. But that doesn't answer the question why, okay? So to answer this question, we have to find out a few more things. And those things are that the air above your head right now has some weight, okay? There's some weight pressing down on your head right now due to the air. This weight acts as a force on the Earth, okay? It's a force over the entire Earth. And the amount of force exerted over a given area of surface is called the atmospheric pressure or air pressure. So the air pressure is the amount of force exerted over the surface, or over a given surface in a specific area. Okay, and it changes. It does vary slightly, you know, obviously from place to place. But anyway, the bottom line is that there's this air pressure or atmospheric pressure, which is a force that's being exerted on the surface. So as we climb in elevation, the mass above us Okay, so as we climb, the mass above us decreases and therefore pressure declines. Okay, so the amount of air or the amount of atmosphere above our heads that's causing this force actually decreases. Okay, so pressure declines. Because of the greater pressure at the surface of the Earth, the density of the air is higher. Okay, because there's greater pressure, greater density of air, and both density and air pressure decrease as altitude increases. Okay, the change in air temp is a bit more complicated though. So air temperature normally decreases from the Earth's surface to approximately 11 kilometers. Okay, the rate at which it decreases is called environmental lapse rate. So the rate at which the air temperature decreases as you increase your altitude is called environmental lapse rate. Okay, and the decrease in temperature is the result of two factors. One is the higher density air at the Earth's surface allows for more molecular interactions. Okay, it allows for more collisions between air molecules generating heat. Anytime you have collisions, there's going to be a generation of heat. Okay, so the higher density air at the surface has more molecular collisions, so it's generating heat. And second is the corresponding decline in the warming effect of the Earth's surface. Okay, so there's this corresponding decline in the warming effect of the Earth's surface. And as air at the surface warms, it becomes more buoyant. Okay, buoyant means it's going to rise. Okay, and as it rises, the decreasing temperature causes it to expand and cool. So as the air rises, pressure causes it to expand and cool. Okay, the decrease in air temperature through expansion is called adiabatic cooling. Okay. So that's the decrease in air temperature through expansion. Okay, and the rate of temperature change with elevation is called adiabatic lapse rate. All right. So I think I'm going to stop there, and I think I'm going to do another video that finishes up this information on climate. Okay.